Okay, so since we didn't have a lot of time in class to do these notes, I am making this video. It's in your phases, energy, calorimetry packets that we got in class. So to go over, energy is the ability to do work or produce heat. Okay, so energy is there for any type of transfer of doing work. The units consist of joules, calories, and nutritional calories, which have a capital C, while regular calories have a lower c. Capital calories are 1,000 times bigger than little calories, and there are 4.184 joules in 1 little calorie. So let's see how that works. In our example, it's asking how many little calories and joules are in 130 nutritional calories. So we set up our dimensional analysis. We have 130 calories. 1 calorie is equal to 1,000 little calories, which means there are 130,000 little calories. But then we go one step further. 1 little calorie is equal to 4.184 joules, and that gives us 543,920 joules, or 5.4 times 10 to the 5th joules, or 540,000 joules. Okay, so these conversions between them, we use joules in our chemistry classes, and we use calories for our food, so you'll need to be able to go back and forth. Next are the types of energy. So types of energy, we have chemical potential energy, chemical kinetic energy, and nuclear energy. Chemical potential energy is the energy stored in chemical bonds. That's where all of our energy for chemical reaction comes from, is from the bonds. And then when we break those bonds, we produce chemical kinetic energy, and that chemical kinetic energy gives us the reactions that we see every day. Nuclear energy, of course, comes from the nucleus and produces a lot more energy than our chemical bonds breaking. So law of conservation of energy is just like law of conservation of mass. Energy can't be created or destroyed. So if you remember, right, we had the steel spheres that we hit, potential energy to kinetic energy to heat energy. Energy is always conserved, it's just transferred to different places. This one is important. So what is temperature? Temperature is a measurement of average kinetic energy of molecules, whereas heat is the actual energy that is being transferred. Okay, so temperature is a measurement, heat is the energy. So don't let those two things confuse you. Alright, now that we know about energy, we can look at calorimetry. Calorimetry is how we see how many calories are in our food, how much energy is released from a certain reaction, anything like that. So the first definition we have here is heat capacity. Heat capacity is a measurement of the energy it takes to raise a substance by 1 degree Celsius. So heat capacity is kind of vague. It just tells you that you need to be able to raise the temperature by 1 degree. However, if we look, there is another one, and this is the definition we use more, is called specific heat. Specific heat is the amount of energy it takes to raise 1 gram by 1 degree. So it's a bit more specific. It tells us exactly how much energy we need when we're talking about a substance, when we're trying to change the temperature. So if we have 1 gram to raise it 1 degree Celsius, that's how much energy we need. That's what specific heat means. So if you look over here where it says specific heat of water is 4.184 joules per grams degree Celsius, what that number means is that there is 4.184 joules. If I have that much energy and I put that much energy into 1 gram of water, it'll raise by 1 degree Celsius. So that's what specific heat means. Now, if we look down here, we're going to skip this part for just a second and go down here. We have the heat of a substance is equal to mass times the change in times the specific heat times change in temperature. Okay? So whenever a question is asking you for heat, or you want to know the heat of a system, you want to know the amount of joules it has, anything like that, you're going to use this equation right here. So heat equals mass times specific heat times change in temperature. The change in temperature is usually in degrees Celsius, The specific heat is in joules per grams degrees Celsius, just like we see up here. Mass is in grams, and heat is in joules. Okay? So when we're talking about something letting off heat, there are a few words that we need to know. And those words are system, surroundings, and universe. The system is the part of the process that you are looking at. It's what's either losing heat or gaining heat. It's the part that you are watching. So if I take a hot metal sphere and I put it into a cup of water, the sphere is the thing that I'm watching. I'm watching the sphere let off energy into the water. And the water is absorbing the energy from my still sphere. And that is what we call the surroundings. So the surroundings is anything that is outside the system, that is either absorbing or giving up heat. Then the universe are when you put those two things together. So let's say I had a cup with water in it. I put my steel sphere inside the cup. The steel sphere is what I'm looking at. It's my system. I'm seeing the heat leave. The water is going to absorb the heat that has left, so the water is my surroundings. And the universe is the water and the steel sphere. So let's go back up here where it says heat of reaction is equal to negative heat of surroundings. This is simply saying what we said with our water example. Whatever heat my reaction lets off, my surroundings has to absorb. Heat can't disappear. It has to be conserved. So whatever heat is being let off, the surroundings has to absorb. So that negative sign doesn't actually mean like a negative number, like it's on the opposite side of your number line, like it does in math. That negative sign just means that you are releasing heat. So if you have a negative sign on your heat, that means you're releasing heat. If you don't have a negative sign, if it's positive, that means you're absorbing heat. All right? So let's look at our examples. In our example, you can read that we have 1 gram of hydrogen, and that's going to make HCl, and it's in 500 grams of water, and the temperature rises from 25 to 29.24 degrees Celsius. Now this is asking me for the heat absorbed. Well, I know my water is going to absorb the heat, so I want the heat of my water. Whenever a question asks for heat, I'm going to use my exact same equation. Q equals mc delta T. That's the equation I use. So I have my heat of water. Now if I want my heat of water, well, which mass do I use? The hydrogen or the water? You probably guessed it. It's the water. I need the mass of water in order to find the heat of water, which means I need the specific heat of water and the change in temperature of water. So whenever you're using this equation, Q equals mc delta T, all of your pieces need to be of the same thing. So they all need to be for water. They all need to be for the potato chip. They all need to be for the solution. They all need to be for the reaction. Whatever you choose to find heat for, everything has to match up. So if we look at this, I have 500 grams of water. The specific heat of water is 4.184. I had that up above in my notes. And then I take my final minus initial temperature, which gives me about 4.24 degrees Celsius. I multiply those together and I get 8,870 joules of energy. So that's how much energy was released when that reaction happened, when hydrogen reacted with chlorine. And there you have it. So if we come down here, I have a 14.23 gram sample of potassium chloride. I'm going to put it into water, and then I'm going to do the same thing. Temperature change, and I want to know my heat. If I want to know my heat, I'm using Q equals mc delta T. I take my mass of my water, because that's what I want to know. I want to know how much heat is released. So mass of my water, specific heat of my water, change in temperature of my water, and I multiply those together, and I get a negative 4,443 joules. Now, if you recall from us talking before with the heat of surroundings and the heat of reaction, remember that the negative sign isn't meaning that it's a negative number or it's not releasing heat or it's, whatever. It's not a negative number. That negative sign just means that your reaction is releasing heat because you get a negative heat symbol. So a negative means release, whereas up here you have a positive number. That means that my water absorbed that energy. Alright, so negative release, positive absorb. Alright, final example. What is the specific heat of aluminum? And they give us our information. Well, specific heat I know is dealing with heat. They give me my mass, my change in temperature, and my heat, which is Q equals mc delta T. So I can use that equation again. Now, since I only want specific heat, well, I need to get specific heat all by itself. So Q is joules. Q is always joules. Heat is joules. So I put my 207 joules here. Mass is in grams, so 28.4 grams. Specific heat is what I'm looking for, so that stays the same. And then 8.1 degrees Celsius. That's my change in temperature. It said it increased by 8.1 degrees Celsius. So then, I need to multiply 28.4 times 8.1 and take 207 divided by the answer to get C by itself. And I end up with 0.899 joules per grams degrees Celsius. So these guys, all right here, are just using that Q equals mc delta T. And we need to become very familiar with that equation because we're going to use it a lot. It's how you calculate a lot of other things. Heat is very important to us in this unit. So, go over these, make sure you know them, and then on your homework, you're going to practice. Alright. And then the real world examples down here. Real world examples, why do we care? Specific heat deals with a lot of things. It regulates our temperature on land. It can cause things to burn but not burn, like when you put hand sanitizer on your hand and it burns. Well, hand sanitizer is made out of alcohol and water. The water doesn't heat up as fast, so it protects your hand. But the alcohol will burn because it has a very low specific heat. It's very easy to transfer energy to it. So all of these different things, there's a lot of examples, but the reason why we care is specific heat has a very big impact on our lives. It's why we sweat. It's why we use water to help us cool down. Water absorbs the heat where our body can leave it off. So that's why we care. All right, those are the notes. Let me know if you have any questions.